Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking at the cumulative geometric distribution. So this is a sequel video to the first video that I've got on the geometric distribution. I'll make sure that I leave a link in the description below for you to go and check that out. So in this video we're going to assume that you already know what the geometric distribution is and what it means if a random variable has a geometric distribution. Okay. So just to remind us, if x is geometrically distributed with this parameter p, then the probability that the random variable takes the value little x is p times 1 minus p to the power of x minus 1, okay? And just again as a recap to explain a situation that might have a geometric distribution, in general we're talking about a situation where the probability of getting a success is p, it's constant, and x, the random variable, is measuring the number of trials or attempts that you require before getting your first success. So as an example, we could be talking about rolling a normal fair die over and over and over again until you land on the number 4, for example. That would have a geometric distribution. And x would be counting the number of rolls that you need, okay? And you might want to work out what's the probability that I get the number 5 for the first time after 3 rolls, or on the second roll, or on the 4th roll, or something like that. So today we're going to look not at the probability that x is equal to little x, but we want to come up with an expression for the probability that x is less than or equal to this fixed number little x. So I want to come up with some sort of expression that maybe looks a bit like this one, that's describing the probability that it takes me, let's say, less than 3 rolls to get that 5 or that 4 for the first time, or maybe less than 10 rolls before I get the number 6 when I roll the die, or maybe I'm tossing a coin and I'd like to know what's the probability that it's going to take me less than 5 rolls to, or 5 tosses in this case, to land on heads for the first time. Or, you know, you can think of loads of examples. We're actually going to do a couple of examples in this video, so stay tuned for that. But we want to come up with an expression for this. Now, if little x is small enough, you could just brute force it because you could just work them all out. So for example, let's say we wanted to work out in a given situation the probability that x is less than or equal to 3 or something like that. Technically, you could say, well, this is just the probability that x is 1 plus the probability that x is 2 plus the probability that x is 3, right? Like technically you can do that, and that's basically a simpler version of what we're going to do. But of course, what if you want to work out for some sort of complicated situation the probability that x is less than or equal to like 100 or something? You don't want to have to do this every time. So we're going to come up with an expression right now to explain it and to describe it. Okay, this is what we're going to do. So in the exact same way, remember this is just saying the probability that x is 1 plus the probability that x is 2, all the way up to and including the probability that x is this number little x. So really, we're just trying to work out an expression for this. And if I replace all of these probabilities with just the expression that it actually is, so the probability that x is 1 is just p times 1 minus p to the power of 1 minus 1. And that's the power of 0, which is 1. So it's just p times 1. So this expression here is just p. On an intuitive level, the reason why this is true is if you're rolling your die and it only takes you 1 attempt, then the probability of this happening, only taking 1 attempt, is just the probability of getting that thing on the die. Okay, so or whatever your situation is. So the probability of immediately getting a success is literally just p, almost by definition. Okay, then the next term is going to be p times 1 minus p to the power of x minus, or to the power of 2, sorry, minus 1. So to the power of 1, like this. The next term is going to be p times 1 minus p squared, and this is going to go on and on and on, all the way up until we get p times 1 minus p to the power of x minus 1, okay? And basically all I want to do is come up with an expression for this. Now, luckily, this is actually, once again, this is a geometric series, which is really nice because a geometric series has a nice formula for it. So what do I mean by that? Well, it's a geometric series where the first term, I'll call it u1, is p. And the common ratio, remember from a geometric series, the common ratio is just the number that you times by to get from one term to the next. In this case, it's 1 minus p, okay, because we're timesing by 1 minus p to get to each of the next terms. And that's everything that we need, okay? And how many terms are there? Well, there's x terms in total, right? Because this is to the power of x minus 1, but this term here is like the 0th term, x to the, or 1 minus p to the 0. So in total, there are x terms. So the number of terms, n, is x, okay? And then I'm gonna write it down over here. The sum of the first n terms of a geometric series is u1 times 1 minus the common ratio to the power of n divided by 1 minus r, okay? Hopefully we know this formula. This is just the formula for the sum of the first n terms of a geometric series. Okay, so just basically using that, we can see that all of this is going to end up being equal to u1, the first term, that's p, so p, times 1 minus the common ratio, which is 1 minus p, to the power of x, like that, divided by 1 minus the common ratio, which is 1 minus p. Okay, like that. And then we just simplify it. So what have we got? Well, on the numerator, we've got p, and I'm going to keep this in brackets for now, 1 minus p to the x. Oh, no, that's right, yeah. What am I? Yeah, no. Overcomplicating it. There we go. So that's not even changed, but the denominator can change, right? Because it's 1 minus 1, and then there's a minus p, so it ends up just being p on the denominator. And then the p's cancel out, right? So assuming that p is not 0, it's not going to be 0 because that's not even a probabilistic situation anymore. If the probability of something happening is 0, then you're not even talking about probability anymore because it's just deterministically not going to happen, right? So p is not going to be 0, so we can divide both top and bottom by it. And we end up getting our final thing, which is 1 minus p to the power of x. So what this is the probability that the random variable takes a value less than or equal to a number of your choosing, x, okay, lowercase x. So this is our expression for the cumulative distribution, okay? Now we're going to look at how to actually use it in a real question. Okay, so it's a bit wordy, but we can read it, it's all good. So Mr. Beast does a challenge where the first person he approaches in a shop that's subscribed to him wins $10,000. The probability any given person is subscribed to him is 0.1. What is the probability he finds a winner in 4 people or less? So that means he's going to go around the shop, he's going to go, hey, are you subscribed to Mr. Beast? And they're going to show him their phone, and if they're subscribed, they instantly win, and if they're not, he moves on to the next person and asks them. What is the probability that after 4 people, he has found a winner, okay? He's found a winner after 4 people or less. So the first person, second person, third person, or fourth person that he answers is a winner. What is the probability? Okay, so first of all, we need to define our random variable, okay? So I'm going to say that let x, capital X, represent the number of people or shoppers that Mr. Beast asks before and including winning the money, or giving away the money, I should say as well. Giving away the money. Okay, so that's x. So a bit of a setup. I appreciate you guys' patience with that. Bit of a long setup, but we are ready now. Now we can say the important part is that x is going to be geometrically distributed, and the probability P of success in any given trial is 0.1. Okay, 0.1. Now we can use the formula. The probability that the random variable is less than or equal to our number, we're choosing the number 4 here because it's in 4 people or less, is given by that formula there. So we're looking for the probability that x is less than or equal to 4, and it's just going to be a simple case of using the formula. So we're going to have 1 minus 0.1 to the power of 4. So notice there's no x minus 1 in this one. There's an x minus 1 in the top one, but not in this one. Okay, and that's equal to 1 minus 0.9 to the power of 4, like that. And if you want to know what 0.9 to the power of 4 is, or 1 minus it, is 0.3439. So this whole answer is 0.3439, okay? So the probability that he needs to ask 4 or less people before giving away the money is 0.3439. So chances are he will be asking 5 people or more. Let's look at one more example. Okay, so I like quacking at ducks, but the probability that any given duck will quack back is only 0.25. What is the probability I need to quack at more than 5 ducks before a duck quacks back? So as you can see, we're dealing with some pretty pressing matters in this video, but this is the setup for the question, okay? So the difficulty with this one is there's 2 things. First of all, be careful. I need to quack, what's the probability I need to quack at more than 5? There's 2 important things in that little part there, okay? First of all, more than 5 means 6 or more, okay? And also it's more than, not less than. This formula tells us the probability that we're looking at something less than a number, not more than it. So we have to slightly manipulate this. So I'm looking at the probability that my random variable, and I should define the random variable as well, actually, just to make it nice and rigorous, just like last time. So I'm going to say, let x represent the number of ducks I need to quack at before the first duck quacks back. Okay, that's what we need to define our random variable to actually be. Again, before we start going on about the probabilities, let's say that x is indeed geometrically distributed. The probability that any given duck will quack back at me is 0.25. So that's going to go here, 0.25, like that. And now we can then say, okay, well, we're looking for, in this question, the probability that x is bigger than 5. And normally in statistics, you want to deal with like bigger than or equal to's or less than or equal to's. So I'm going to say x is greater than or equal to 6. That's the same thing as x is bigger than 5, because x can't be 5. It needs to be more than 5. So I'm talking about 6, 7, 8, 9, 10, etc. And again, I can't directly use this formula because the inequality signs are the wrong way around. But what I can do is I can say that the probability that x is bigger than or equal to 6 plus the probability that it's less than or equal to 5, together these add up to 1, because these are these are all of the possible things that could happen, right? Either x is bigger than or equal to 6, or it's less than or equal to 5. So the sum of all of those probabilities should add up exactly to 1. That means that the probability that x is bigger than or equal to 6, this is what we're looking for, is 1 minus the probability that it's less than or equal to 5. And the reason I've done this is because now we can use the formula, because do you see here we have the probability that x is less than or equal to something. That's what this formula is actually for. So I can say this is equal to 1 minus the probability that x is less than or equal to 5 is 1 minus 0.25 to the power of 5, like this. Okay, so there's a lot of like 1 minus, 1 minus, 1 minus, but this ends up being, I'll do it here, 1 minus 1 plus 0.75 to the power of 5, okay, or 3/4 to the power of 5, and that ends up being 243 off the top of my head divided by 1024. 243 over 1024. That is it. If you want it as a decimal, it's roughly 0.2373. Okay, 0.2373. But this is how I would leave it, just as a fraction. So this is the probability that I need to quack at more than 5 ducks before the first one will quack back at me. And we're going to finish off this video with one more thing. Okay, because I've done something quite interesting, and you might say, well, you've come up with a formula for less than, and you've just used greater than. Why don't we come up with a formula for greater than as well? And that's a nice segue into actually doing that right now. Okay, guys, so what we're looking for is a formula for the probability that the random variable is bigger than or equal to little x, okay? And again, we can use this manipulation to say that this plus the probability that big X is less than or equal to x minus 1 has to add up to 1. And just sit with that for a second, make sure you're happy with this. So either the random variable takes a value bigger than or equal to some number x, or less than or equal to 1 less than that number. Okay, so in the last example, x here was the number 6. So it was bigger than or equal to 6, less than or equal to 5. Okay, so 1 less than it. But in general, we're looking for this. So we have that the probability that the random variable is bigger than or equal to x is 1 minus the probability that the random variable is less than or equal to x minus 1, like that. And actually, we basically just have a formula for this already. The only difference is that we have to replace the x in that formula with x minus 1, and then we're kind of done. So we've got 1 minus, and then big brackets here, 1 minus p to the power of x minus 1. I'm replacing the x with x minus 1 because that's there. And then we've got 1 minus 1, that's 0. I'll still write it out though, 1 minus 1, and then plus 1 minus p to the power of x minus 1. And you can see the 1 and the minus 1 just cancel out, and you end up with 1 minus p to the power of x minus 1. And again, this is the probability that the random variable takes a value bigger than or equal to a number little x. So feel free to, make a note of this formula, this equation, and try the previous question by just directly using this, and you'll still get the same answer of 243 over 1024. So now we also have, and we can add it to the little collection here, that the probability that x is bigger than or equal to little x is, as we see here, 1 minus p to the power of x minus 1. How fun is that? I think it's pretty fun. So in the next video, we're going to look at the mean and the variance, or the expected value and the variance of the of just the geometric distribution. Okay, and that video is going to be a bit crazy. So make sure that you're really, really happy with stuff like differentiation and just algebra, because it's gonna get crazy. If you're interested in just doing crazy stuff with like differentiation and stuff, definitely check it out. That will be out very soon. Link in the description to that as well. Thank you guys, as always, so much for watching, and I'll see you in the next one. Cheers.